Okay, so for today's lesson, we're going to mainly talk about the more advanced techniques of integration. So the three things we're going to talk about is long division, completing the square, and partial fraction decomposition. The first one is the long division. It's usually the algebraic long division we talked about in Algebra 2 and in pre-calc. So you're usually looking at rational functions where the numerator is larger than the denominator. And your results usually come out with a logarithm in them. So that means when you integrate, you end up with a logarithm. And the second one here is the completing the square. Your results usually have arctan in them. You'll see in a bit. But when we talk about the completing the square, it's usually in the denominator. And the last one is the partial fraction decomposition. It's probably one of the more challenging ones. It gets really difficult really quickly. But we'll see how far we get from here today. So the first example we're going to talk about is long division. Okay? Our example here is integral of x cubed plus x divided by x minus 1. As you can see, the numerator is larger than the denominator in its degree. So we have to use algebraic long division. So what you have to realize is when we do this long division stuff, make sure you don't mess up. Because when you mess up, everything's going to go down pear-shaped and mess up. That means you have to redo the whole question. So I will probably align all the x squared together and then put brackets here. So that means the minus and the plus, and you'll make the less mistakes you'll make in this question. So when you do algebraic long division of this divided by that, you end up with x squared plus x plus 2 over x minus 1. So from here, we can just replace this with what we just found over here. As you can see, the first three terms here are just monomials. You can use the power to integrate them. And the last one here is 2 over x minus 1. And then in this case, you end up with a logarithm over here. So in that case, x squared, x cubed divided by 3, x becomes x squared divided by 2, and 2 integrates to be 2x, and then 2 over x minus 1. X minus 1 is a degree of 1, and that means you can use the log. In that case, the 2 goes out as a constant, and then don't forget your plus c over here. Okay? The second example for long division is x squared divided by x squared plus 1. And in this case, again, because they have the same degree, so I should probably write over here that they have to be equal or greater than. So in that case, if you do a long division here, you end up with 1. Going to there, you have minus 1 because to subtract 0 minus 1 is negative 1. And then you end up with this. Okay, as you can see over here, the 1 here is easy to integrate. It just becomes x. And then the plus, in this case minus, 1 over x squared plus 1. As you can see, this is an arctan we've integrated. And then because this is a 1, remember, when you have a 1 here, you have to have a 1 here to do the substitution for arctan. So when you do that, you end up with x minus arctan of x plus c. Okay, that's what you have. Don't forget the plus c. It's very important. Okay, the next one here is completing the square. But when we talk about completing the square, look at the denominator. As you can see, when we complete the square in the denominator, we want it to look something like x squared plus 1 in the denominator. In other words, you're looking at the arctan integral. Okay, so completing the square for the denominator, we have the first example, 2 divided by x squared plus 2x plus 2. Okay, integrating with respect to dx. However, as you may have already noticed, this doesn't qualify for this one. So in that case, you can't use your algebraic long division. So first thing you got to do here, complete the square in the denominator and take the constant out. If you complete the square here, it's just x plus 1 squared plus 1. And then make sure, be very careful. This is a plus 1. Okay, it has to be a plus. If it's a minus, then we have to resort to partial fractions. As you'll see in a little bit why we have to do that. Okay, so doing this, we make a substitution here because this is my x squared plus 1. That's not very nice. So we make a u substitution, u equals x plus 1, and then because du dx, if you differentiate, they're equal to each other. So now that we have this, we have the integral of 1 over u squared plus 1, and then 2 on the outside, and this is a substitution. Okay, this is arctan. Okay, I messed this up. This is arctan. Okay, so this is arctan of u, and then because this one's arctan, you have to bring back your u, you'd use x plus 1. So in that case, this one will end up with arctan of x plus 1 plus c. Okay? Again, don't forget the plus c. If it's not, you don't have initial conditions, you cannot lose that c. Okay, so in the second example, this one's a little more challenging because of the numbers we'll be dealing with. And in this coming example, this is not going to be a plus 1 anymore. It's going to be something messy. So this is where algebra comes in. You have to be very careful. So my example here is integral of 1 over x squared plus x plus 1. Okay, by completing the square, it's the middle term divided by 2 squared. In that case, it's 1/2. And because we added an extra 1/2 squared, we have to take it away. So you have negative, you have to subtract 1/4. So in that case, once we have simplified this, we have integral of x plus 1/2 squared plus 3/4. And first thing here, we want to simplify the 4. So we move the 4 outside in front, multiply everything in the denominator by 4. We have to do it with the 4 in the numerator. So we end up with this over here. And then when we're done with that, again, x plus 1/2, that's kind of nasty. So what you want to do here is make a u substitution. U is equal to x plus 1/2. Okay? And then again, du dx, if you differentiate it, you get equivalent statements. So du is equal to dx. Okay, now, looking at this, we end up with 4 on the outside, 4u squared plus 3. Again, this 3 is the thing that's troubling us. So that means we have to move the 3 to make it look like a 1. So in that case, we factor out a 3. That means we have to multiply this term by a 3. So, because what we did here, we have to combine it into the u. So in that case, the 4 here, take the square root of 4, which is 2, and then the 3 that you divided out, you take the square root of that, because root 3 squared is 3, 2 squared is 4. In that case, we come back over here. Because we factor out the 3, we have to put the 3 out here. Now, again, because this is a nasty term, we have to use another substitution b. So in that case, you have 2 over root 3b, u, and then differentiate, you end up with this, and we write in terms of u. So in the case, du is equal to root 3 over 2 dv. Now, because we have to substitute this back out into this equation, in that case, my du is equal to that. So that means I've moved my constant out, so root 3 over 2 is over here. And my v is equal to my 2 over root 3u. Okay? Now, looking at this part here, this part is very easy to integrate. Okay, this just comes out as arctan of v. And this part is just a constant. In that case, simplify gives us 2 over root 3 and arctan of v plus c. But because the question is in terms of x, we have to substitute our variables back. But as you can see, we do substitution twice. The first time here, we made a substitution of u is equal to this. So, and the second time, we have v is equal to this. That means we have to bring it back. So in that case, put this back into v, and then for your u, substitute back x plus 1/2. In that case, you end up with 2 over root 3 arctan of 2 over root 3 x plus 1/2 plus c. Okay? Don't forget your c. Okay? That's all for completing the square and long division. The next thing we're going to do here, we'll be doing at partial fraction decomposition. Okay? See you in the next video.